Okay. So please silence your cell phones. That's something I'm guilty of sometimes. So doing it myself. So introduction for San Francisco Bay ACM. So we're a local chapter of ACM. That's a professional society for computer science. So anytime with the computer science journals or conferences, they'll be through ACM. So that's the world headquarters is in New York. That was founded in 1947 in the Bay Area. We're a local professional chapter in the Bay Area, and we were founded in 57. And we tend to have upcoming talks on our meetup channel. So we are up to over 13,000 people on our meetup page. So if you want to give a talk, there's a big audience you can promote to. We have about 260 past talks on our YouTube page. So we have a lot of good content. If you like tonight's talk, you might find other content that's of interest there. So we try and have 2 monthly meetings, generally third Wednesday of the month, fourth Monday of the month. If you want to volunteer with us, we might have a planning meeting earlier in the month that you could join, and we're happy to have that. So I'd like to thank a couple of our sponsors. We have a location sponsor for here at Valley Research Park. So they are renting suites for startups. Also, RXM is a cloud-native AI training and consulting business. So if your company might need, say, a week-long training in Kubernetes or some in-depth topic for a large developer team, then that's the kind of thing that you can talk to them about. So they have a variety of domains, but they can travel to your site and location. Hi, people in the back, there's lots of chairs up front, because if you ask questions, okay. Oh, I promise I won't bite. Okay. I'm not saying the front row, I'm just saying the front 6 rows on the carpeted area. Another sponsor is Front Egg. So they have managing cumbersome identity management. So I'll be over here monitoring the chat in Zoom. So if anybody that's a remote audience member wants to ask a question, I'll be watching the Zoom chat. And I can ask the speaker those questions. Also, if you're here physically present and you ask a question, we ask the speaker to repeat the question for the recording and remote people, because the PC won't be able to pick up your question. So no 5-minute questions, because the speaker won't remember it and be able to answer it. I mean, because I ask him to repeat the question for the audience. So be kind to our speaker. You can always ask a second question, no problem. We have a call for volunteers. You can start with a limited engagement with a little bit. If you like something more technical, you can work on some of the technical back end of things, marketing or other kinds of things, member database. If you like something more outgoing, I like to invite speakers. I'm always a curious person. So that's a way I type of volunteer. Liana works with a lot of volunteers for food and logistics. So there's different ways we work as a nonprofit. We have an honor system jar for food near the pizza. So some upcoming ACM events. So next Monday, Liana? Well, I'll talk to her later. We'll have likely have a meeting here deploying scaling large language models in the enterprise, architecting multi-agent systems, integrating with vision, data, and responsible AI. So we have about 270 people signed up for this. So again, usually there's a lot of remote people, but there should be a lot of people local for that. So that's a data science talk. Then in November, we're going to have a designing for scale, reliability, and resiliency, real world lessons from building high throughput systems by an engineer in DoorDash. And then we have a January talk, taming tech debt for platform reliability. And then we may get some other talks scheduled in between then or sooner as well. So just watch our meetup page. So I'd like to introduce tonight's speaker, from collision to discovery, machine learning at the Large Hadron Collider. So the Large Hadron Collider is a 27-kilometer long ring below the French-Swiss border, and it's helped discover the Higgs boson, among many other things. The detectors at the LHC gather data at 60 terabytes per second. I've never heard of anything so big. This is cool. Discuss how machine learning supports scientific processes and shed light on 95% of the universe that still lies in the dark. So that was a nice phrase that you wrote in the description. I'm about our speaker, Dennis Noll. He's a postdoc researcher in physics at Stanford University. He's a member of Professor Nachman's research group. He likes to focus on smart, fast, and reproducible physics analysis. He's an expert in Higgs boson research. He's pioneering AI-driven methodologies to detect anomalies within the vast data generated. So please help me with a warm round of applause for tonight's speaker.
Yeah, thank you very much for the nice introduction. It's great to be here. It's great to talk about my favorite subject in the world for the last 10 years-ish or so. And I've prepared a presentation which goes really from the initial data taking to how we extract results at the LHC. And really excited to talk to you tonight. All right, let's get started. I was already introduced a little bit. I want to say some more words, why I'm here, why I talk to you, and take the microphone. Now it's on. All right, so I'm a particle physicist. I did my training in Germany, did my PhD in Germany, and then I came to Berkeley Lab like 2 years ago. And some month ago, July 1st, I switched to Stanford University, and I'm a third-year postdoc there now. I'm doing physics mostly. On the physics side, I'm doing Higgs boson analysis and anomaly detection. You will learn a little bit more about what that means. Then on the computing side, you will see that we have vast computing centers which span all around the world. And I'm doing a lot of high throughput computing and cluster computing. And then on the machine learning side, I'm specializing on both development of new methods and application of known methods to collider data. And I've been doing this for quite some time now. So you'll see the CERN a little bit in a little bit. And we have different experiments at CERN. And the two largest experiments are the CMS experiment and the Atlas experiment. And I've been working for the CMS experiment for like 6 years. And then 2 years ago, I switched to the Atlas experiment. Should say, please feel free to reach out after the talk if you have more questions about the talk or want to discuss about other interesting things in the scope. So now that I told you something about me, I also want to learn something about you. I will ask 2 questions, and we'll do this by hand sign with the audience in the room only. So the first question is about how experienced you are in machine learning, because we will have a lot of machine learning in this talk. And I'm talking here about like machine learning on the architecture side, loss functions, optimizers. So not so much on using GPT or something like this in your web browser, but really developing machine learning methods. So we'll start with A, absolute beginner. Okay, B, basic knowledge. Means you've done something. Okay, C, you have maybe opened an IPython notebook, trained something. Okay, very good. And then D, expert knowledge, you use it every day, basically. Okay, very good. So very diverse audience and many different knowledge levels here. Don't worry, even if you lift your hand on A and D. For A, you will learn it not from the ground up, and you will learn the most important things. And for D, I hope you won't be bored. I'm sure you won't be. And then the second thing is, how much do you know about particle physics? So I don't know anything about it. Okay. B, you have basic knowledge, maybe read an article in the press, saw about the Higgs boson 2012 and so on. All right. C, you're knowledgeable in a related field. Maybe you study physics, you're a solid state physicist or something related. Okay. Or D, you're just here to ask the hardest question. Okay, nobody. I expect hard questions anyway. Okay, very good. So now that we know each other a little bit, let's get started. Why are we doing particle physics? So I have my water bottle here, and in my water bottle, I have water. Water is H2O, which means I have 2 hydrogen atoms and 1 oxygen atom. If I look closer in the hydrogen atom has a proton in the middle and an electron, which is on the outside. And this electron is already what we call a fundamental particle, which means we cannot split it anymore. If we look in the proton, we can split the proton and we can see, okay, the proton is actually 2 up quarks and 1 down quark. Okay, so this is basically the foundation of particle physics. If we look to the very, very small scales, 10 to the minus 15 meters, then we see fundamental building blocks of our universe. And these fundamental building blocks we have discovered in the last 120-ish years around, we have discovered 17 of them. Now we can group them in the matter particles and the force carriers. And that's from a particle physicist view to the world, that's all that is. So if you look in the whole universe, what we know about the universe is comprised in these 17 particles. You need the up quarks and the down quarks to make protons and neutrons. Two up quark, one down quark make a proton. Two down quarks, one up quark make a neutron. And I can build every atomic core we see on this planet. Then we put electrons in the respective numbers, and we can build every atom we see on this planet. If we have every atom, I can build every molecule. If I have every molecule, I can build every material. So from a particle physicist view, and that's my, personally, well, I love particle physics, that's all there is. And it's not so easy, actually. If it was so easy, we wouldn't need to study, I don't know, 8 years until the PhD. But the actual mathematical model which is behind this is called the standard model of particle physics, and that's like the energy of this model. And I showed you the first third of the first page. If you would write it like this, it would be like 5-6 pages of a formula. But all these particles have a representation in the math which is going on. And that's actually what you learn, for example, if you study physics and specialize in particle physics, how these formula, this model about the universe, translates into the particles and into the rest. So, yes.
Dumb question, but the little springs that are between the quarks,
Yes.
they don't appear at your table. I'm wondering what they are.
Yeah. The question was the little springs which are between the quarks. They don't appear on the table. They appear on the table. I just don't put a label. They're the gluons. They're the force carriers of the strong interaction. Yeah. Okay. Thanks for the question. Very good. All right. So now we have the model. We can describe the whole universe. So we're happy. Why are we investing money in the LHC, and why are we doing the experiments? Because in reality, we're not very happy. We're actually motivated because standard model of particle physics describes the visible matter, the 5% of the universe. If we look above the boundaries of Earth, if we look how fast galaxies rotate, for example, or how fast the universe expands, so on a cosmic scale, we see that these 17 particles only describe 5% of the energy content of the universe. We know this because, for example, if we look at a galaxy, we can calculate how heavy the different stars in the galaxy are, and we can, with our knowledge of gravity, which is quite good after Einstein told us what the general theory of relativity is, we can calculate how fast could the galaxy rotate. And we can see, oh, it rotates much too fast. So there has to be something else, something we have not found yet. And this is what we describe by dark matter. We're not very inventive with the model, with the name. We just call it dark matter because we cannot see it. That's why it's dark. And then 68% of the energy in our universe are dark energy. That's if we put in all our knowledge we have and see how fast the universe could expand, we see this is much, much, much too slow. We actually see that the universe is accelerating with the expansion. And the energy we need to explain this acceleration would comprise 70% of the energy of the universe. So I told you we can describe everything and we know everything, but the truth is we know very little about our universe from like an energy standpoint. And this is
a question. I don't know much about the physics part. The ratio of dark matter 27% to dark energy 68%. Is that ratio similar to visible matter and energy?
To visible matter and energy. So visible matter is energy, basically. If we have, for example, this light coming from the light thing, that you could describe this as energy, but from a particle standpoint, it's a photon. So it's a matter, it's a particle in the standard model which hits your eye.
Well, you were breaking down the dark stuff into matter and energy.
That's right. I said dark matter. You could also call it dark energy. Yeah.
Well, whatever you call it.
That's right. That's right. We call it dark matter. It's just the words, just the words we use for it. Sure. Physicists are very lax with the names matter and energy because E equals mc squared. So energy equals mass times the speed of light squared. That's mostly historic because why we call the one dark matter is because it has a gravitational pull on everything. So we imagine a matter particle. So matter, which has gravitation, and dark energy is mostly historic, the naming. Yeah. Dark matter and dark energy do not necessarily have anything to do with each other. We don't understand both components, but they don't have to be related at all. Yeah. Any more questions? For the physics part. All right. So what do we do now? We know 5% of the energy of the universe. I'm a particle physicist, and as particle physicist, I like to smash things at very high speeds, at very high energies, and that's actually the best answer we've been coming up with in the last 120 years, is to put a lot of energy into the particles that we know, and then collide them, and then we have, I said it before, E equals mc squared, so we have a lot of energy at one point in space, and this energy will transform into mass. And then this mass, we hope, has some particles which are part of the dark matter part, for example. So that's why we go to the Large Hadron Collider, for example, which is currently the most energetic particle collider in the world. It's located right under the French-Swiss border. And we accelerate one stream of particles this way and one stream of particles this way. And then at 4 points, LHCb, ALICE, ATLAS, and CMS, they're collided. And then we have big cameras around the collision points. For example, that's the CMS experiment I was working on before. These cameras basically capture the new particles. So they capture what the collision looks like. The thing we try to study is very, very rare. And you will see later in the talk how rare exactly it is. But because it is so rare, we need to do these collisions very, very often. And we're actually doing them at a whooping frequency of 30 million collisions per second. And the whole detector has about 100 million readouts, and that equals roughly to 60 or 80 terabytes each second, and leaves room for very, very exciting data analysis. So now I want to show you a little video, motivational video. We'll look at the video first, and then we go to the question. So we have pre-accelerators, and these pre-accelerators used to be the most energetic accelerators at their time, but now we use them just to pre-accelerate particles to go in the Large Hadron Collider, which you can see now, so a 27 kilometers circumference. And then here you see now the ATLAS experiment coming up. The proton is, as the standard model of particle physics, is crossing the French-Swiss border right here. Particles go so fast, they go almost the speed of light, so they cross the border quite often. I don't know if they need a passport. And then at the ATLAS experiment, for example, they're collided. And what these collisions look like, you will see now. So if two bunches of particles collide, they hit head on and new particles are created, and these new particles directly decay into other particles and so on. And then they hit all these different segments of the detector and elements of the detector. And that's what we take the picture of at the rate of 30 million each second. The other question?
Question was, what are the detectors actually?
Yeah.
I mean, are they detecting electromagnetic?
Yes. Yes. So the detectors, the question was, what are the detectors actually? And we can go after the talk maybe in more detail about this. But these detectors are taking multiple properties of particles which pass them, and different particles pass these detectors. So for example, in the middle, we have the tracker, and that's the most granular thing. That's a silicon, high density silicon detector part. So it will just track when an electromagnetic particle passes this detector. And then further out, we have what we call the calorimeters, which are completely absorbing the particles and measuring the full energy of the particles. And then in CMS on the outer side, we have muon chambers, which are like gas filled chambers, which have little wires. And these wires have a current. And if a particle passes, it ionizes the gas. And then it tracks if a particle comes through. Any more?
Question. When you do an experiment with this, you showed it being taken from the small one and then being pumped up into larger rings. Is that done as a single pass or is it continuous?
Yeah, the complete delivery of particles is continuous. The question was, thank you very much, is it a single pass of a particle or is it continuous? And the particles are going around continuous on the scale of hours. So we talk about fills, and we fill the whole detector. It takes like 1 hour, 2 hours, and the whole accelerator, and then the particles go round and round and round for hours, and they collide. The particles which collide, they cannot be used anymore because they collided, but there are enough particles in the collider to be run continuously. Yeah.
Sorry. So for those things that aren't charged, then do you just do some sort of arithmetic to
Yes,
fix up?
that's a great question. So for those particles that are not charged, depends on which particles, they can be simpler. Because if you have a photon, for example, the photon will not interact with the electromagnetic thing, which is the same reason why Wi-Fi is going through, right? It does not interact directly with the silicon, but the electron is then showering in the electromagnetic calorimeter, and the particles out of this shower are completely absorbed. Yeah. So, and the trace of the photon then straight points back to the interaction point.
But something like a neutrino that doesn't interact.
Yes, and there are particles like the neutrino, for example, and it just fly out of the detector, and we have to do a lot of like data analysis and so on to recover what the missing transverse energy in this case is.
Can this detect all 17 of the particles?
Excuse me?
Can this detect all 17 of
Um,
the particles?
Yes, it can. The question was, can the detector detect all 17 of the particles? Most of the particles don't even reach the detector because they decay before. But then from the decay products of the particles, we can deduce back to the particles, and that's actually how we measure them. Yeah.
I just missed the readout number earlier.
Yeah.
100 million
Yeah, about 100 million. Yeah. Per detector.
per detector.
Yeah, 100 million. Most of them are in the tracker. Some are on the outside as well.
Is that per second or what?
They're continuously taking data, and we clock them with like 30 million each second, so that they match the number of bunch crossings in the detector. Yeah. Okay, very cool. All right, let's go on, because now we want to look at exactly how the data analysis is done. So our goal is to find the remaining 95%. And we know pretty detailed things about the 5%. So at some point, the 5% should interact with the 95%. Otherwise, we can never find it, right? If there is something in the universe that never interacts with me, I can never find it. So our hypothesis is that what we have, how we describe the 5% currently, there must be something not 100% right. So there must be some frontier at the 5%, which connects to the remaining 95%. And this is why we test the 5% that we know as accurately as possible for us in this universe. And we do this by having the theory on the one side, and then comparing what the theory does, like how nature looks. For nature, we can do our experiments, so we have the particles in the collider, in the detector, and so on, and we collide them, and we get some data. And for theory, we can make very complex simulations, which are mostly like random Monte Carlo simulations and so on. We'll get more into details with this, and then we can compare. And if the nature, so the black dots, look like my prediction from the model, then everything is looking like my model is telling me. But if there is a deviation, this is actually where it gets super interesting, where I go to my theory colleagues, for example. The theory colleagues will tell me, oh yeah, we have waited years to see this excess, and finally there is the new excess, and we need to change the theory to new theory. And this is the scientific process which we follow. And in my talk, I want to go first on the nature side, then on the theory side, and then on the comparison between both. So we'll start with the nature side. There is a big challenge, and you asked before if you can measure all 17 particles. And actually what we see is not all the 17 particles, because most of the particles that are created in our detector are decaying to other particles before we can possibly detect them in a very messy process. That's like one of the processes, for example, that we see at the LHC. And what we are really interested in is only the red dot in the middle. So that's for us, what we call the hard interaction. And this is when new particles would show up. And everything we see is coming from the 17 particles I showed you before that we know very well. And they produce many other particles, and they decay, and it's a very messy process. And then actually what we...
As a suggestion, if you're pointing things on the slide, the remote audience will be able to see what you're pointing at. You could use a cursor.
Cursor is a good
Then
idea.
everybody can see.
That's a good idea. Thanks. So this is what the red dot is what we want. The green is what is coming out after all the decays, but what we actually measure is the yellow towers, for example. So this is what we have in the calorimeter. So it's a big challenge coming from the calorimeter data. This is the data that we record, up to the red point. There's a lot of like theory calculations, there's a lot of reconstruction and so on that's going into this. And now I want to show you the process in the next couple of slides, how we can go from this to the first information. But first question, before we can do something with the data, is the question, how do we represent the data? I mean, if you're working with some image detection, or if you're working with camera data or something like this, it's pretty easy to say, okay, this is my camera, this is my rectangular grid, and then I have a convolutional neural network or something like this with this regular data. But we have this big detector, which has different granularities at each radius, at each stage. Some detectors are very fast, some are very good in measuring energy, some are really bad in measuring energy comparatively. So the question is, how do we represent the data? Do we represent the data as lists, for example, just like energy hit 1, energy 2, energy hit 3? Maybe that's not the best. Are we representing the data as images? So you can imagine that at some parts in the detector, I can make a slice, for example, and then in this particular slice, I can represent the data as an image. Are we using sequences? So not every time all energy, all the detector parts of my detector are actually firing. So it would be a big waste to save every time if a detector, like if a part of the detector records energy, how much energy or not, because mostly they're empty. But then you also have the question that maybe it doesn't make any sense to have, when I talk about particles, they do not have an ordering, right? I have 10 particles coming out of a collision, and there is no like a priori sequence I can build of the particles. So maybe I should use a set, which is like invariant to the ordering of the different particles. I showed you this process of the decay going from the red blob to the final green. That looks like a tree, so maybe it's like maybe it's good to save the data as trees. Or we go even a step further and do not have like a direct one-to-one or sequential mapping of nodes, and then we go to graph models. And the truth is, actually, all of them are being used at like various different algorithms, and we see a lot of them in this talk. So the first reconstruction going from the yellow towers that we saw to the initial thing is what we call particle reconstruction. And particle reconstruction broken down has 2 steps. So I show on the left here what we see in the detector, and you can see the parts with the different granularity. So in the middle, that's what we call the tracker, very high granularity, and the red blobs you see symbolize how much data or how much energy the single blobs have recorded in a collision. That's one collision. And then on the outside, you see what the calorimeter towers, which have a much higher granularity, have recorded. And we do this in 2 steps. So the first one is the tracking, and it recovers, for example, not photons because they don't interact with the tracker, but electrons, which will go through the tracker. And they combine these red blobs to lines, to tracks. Anybody knows why they're bent, the tracks in this picture, and they're not straight? Yes, we have a giant magnetic fields in each of these detectors, and this magnetic field you look very impressed, but I think they studied physics or something. It's very common knowledge. So if a charged particle goes through a magnetic field, then it gets bent, right? And that's what we use to determine the mass of the particle, for example, because the lighter the particle, the harder it will be bent. Okay, so we have these tracks. All of them are bent. And then we combine these tracks in the second step with the less granular detectors on the outside. And this is what we call the particle flow. And then we get out particles at the end. So first, we'll look at one machine learning application that we do, which is building a graph from the tracker hits. So we have all the tracker hits. This is what was in the slide before, the red dots in the middle. And what we do is, if you have a particle which goes through the tracker, then it will leave some track which is symbolized here by the red dots according to the magnetic field. But we don't know a priori how light the particle was. So connecting the dots to a track is actually a very complicated task because we don't know everything about the track yet. We do this with a machine learning application which is called contrastive learning. Contrastive learning is pretty simple actually. It's like a self-supervised thing where I have my training data set and I would tell the machine learning algorithm, okay, all hits which belong to one particle should be close together in a metric space, and all hits from different particles should be far apart. So my machine learning algorithm will construct me this function which embeds all my hits into this, what we call latent space. And in this latent space, particles which are coming from one track are close together. Particles which are coming from different tracks are far apart. So the next step I can do is.
There was a question, we're like, sure. Did you have a question here after that?
I know, I was sort of thinking, but so no matter what the sort of time resolution of all these detectors are, you can have multiple events
Yes.
in whatever resolution.
Yes. That is a very good. You're asking the very good questions. Everyone here is, but yeah.
Repeat.
Yeah, the question was, whatever the time resolution is, we will have multiple collisions. We work with something which is called, so we work not with single particles. We don't shoot single particles because hitting two particles in the detector would be the task if someone throws a needle from New York and another person throws a needle from Europe and they hit each other in the middle. That's like the precision you need for a single particle. For we use bunches of particles, so they are like thousands of protons which get accelerated together, and the whole bunch crosses the other bunch. And actually, in each bunch crossing, multiple of those collisions happen, and we call it pile up. And the current pile up condition is about 25 to 50 simultaneous collisions. And it's a big problem. It's a big challenge to getting the different proton collisions spread apart. The good thing is that most of these 25 to 50 are not so energetic as the one we're interested in. So we're only interested in the very, very energetic particle collisions, and they have a little bit different features. But yes, pileup is a big challenge for us. Yeah.
It's kind of a physics question, I guess, but if these are these fundamental particles and you're sensing them multiple times across the track, doesn't that require an interaction with a particle that's similar in size to that one?
Yes,
That
so
would like
that's
completely offset
that's
the first observation? Or?
kind of right. So, for example, if you have an electron, the question was if those are the fundamental particles, aren't we changing their path, basically, right, when we detect them? And the answer is that it's partly right. So we interact with the particles, the detector interacts with the particles interact with the detector while going through the detector. But an electron, for example, so those will mostly be electrons, and an electron which goes through a silicon detector will only push out some particles in the silicon detector and then will go on with its path. So it's very, very small. Yeah, but sometimes they interact more strongly with other particles and then they can completely change course, which is also a big change for this program. Yes.
So how is the data actually like physically stored, and like how do you access it? Like I'm imagining there's some giant optical cable that's like the size of my head or something.
Yes. The question was how is the data physically stored, basically? So it depends on which part in the detector you are talking about. If we're talking about these silicon detectors, they are all fed to ASICs directly, like it's our custom hardware. And then this custom hardware feeds to optic fiber cables, and then the optic fiber cables feed on to what we call GPU farms. So then we have a two-tier trigger system, which is like a low-level trigger system, which only makes very, very crude assumptions about particles and only talks about, only looks at total energy in the detector and so on. And a lot of these events are already thrown away at this stage because they're not interesting for us. They're not like the super high energy collisions. And then it goes on to the second, which we call the high level trigger, and the high level trigger then combines different particles from different sections in the detector. We have to do this because combining the whole detector in like at a rate of 30 million each second is just physically not possible. So when I visited CERN for the first time and I was standing in front of the detector you just saw, you're standing there, it's a giant detector, it's 50 meters long, 25 meters diameter. And there is this optic fiber cable you talked about, and it is off again. this optic fiber cable has a length of like 12 meters. And you realize that simultaneously in this optic fiber cable, there are 2 or 3 collisions which are simultaneously in the cable going because just speed of light, right? Okay. I don't know.
I'll see if I can find that.
It's red now as well. Red now.
Wait, so are the data processing, you're just taking a slice and processing it on a laptop, or is this on a supercomputer?
Okay, so all of what I described to you now, we're very, very at the basic steps of the detector. I didn't estimate so many physics questions. It's great to have them. This talks about machine learning. We'll go on. I don't know how much time you have. I love talking about this stuff. We can spend 5 hours. Yeah.
So 9 o'clock, everybody's out the door is locked. If you
Okay.
left something in, then too bad. 'Cause I
All
don't
right.
have a key.
All right. Stay as long as you want.
Most things wrap up by 8:30ish is fine.
Okay, perfect. So the question was, what is the hardware that we use? On the high level trigger, on the low level trigger, like I said, it's all custom silicon wafers and so on. And then you come to the high level triggers where you connect different parts of the detector, and there's a GPU farm with a lot of like commercial GPUs. And then afterwards, it goes on to the reconstruction and to storing systems. And this is like we have a multi-tier system of the LHC, which is called the WLCG, Worldwide LHC Computing Grid. And the tier 0 is standing at CERN and doing it's like a big computing center, like you all know. It is doing all the reconstruction and so on, and it's stored to disk. And then part of it's also streamed to sites around the world. Yeah. Answer your question? Okay. So it's a multi-tier complex system to like cope with the data. Yes.
Just to connect this to the earlier point, this is the 60 terabytes per second. Is that right?
The 60 terabytes per second is actually only what is created in the
Backup.
detector. So if we cannot possibly, if you came to this talk and thought we were storing 60 terabytes per second, I successfully got you here by saying that, but that's like the data rate the detector produces. So if you read the abstract, it's the question was, is that the 60 terabytes each second?
So how much is the actual data that gets stored per second, per minute, per hour?
Yeah, the question was how much is the actual one which is stored. So up until now, the detector has been running for like basically since 2012, but we have upgraded the system and so on. So I would say in the last 10 years-ish or something, we are now at the exabyte thing, but we can but we can talk about more on like the whole scale of the data at the end, maybe, because I have a backup slide for exactly this.
So at that speed at which you're like sampling things, even the latencies in the length of the wires must be full. There
Yes.
must be a lot of engineering.
Yes,
to
there
make
is.
sure they're all the same
The
length.
question was, at this scale, even the length of the wires must be important, and that's right. So if I'm mostly an offline analysis guy, if you talk to like the hardware low-level people, they know everything about like how to couple the wires and so on. Yeah. All right. Any more questions at this point?
So what element is used to create the particles?
The question was, what element is used to create the particles? It's protons. So we take the hydrogen. Okay, another. It's basically. So there's a good story. At CERN, we collide these protons, and actually at the beginning of all the accelerators, there's one hydrogen flask hanging, which is always when the CERN management changes, is always donated by the management. It would hold for like a couple tenth of years or something, but they exchange it for reasons, prestigious reasons.
And the entire tube is complete vacuum, correct?
Yes, the question was the entire tube is vacuum. That is right. Yeah, it's a very, very good vacuum. All right, now that we have some of the physics questions out of the way, please keep on asking them, but I want to bring your attention back to the tracking applications, because now, remember, was some time ago, but we have this contrastive learning, and this contrastive learning embeds all the hits into this contrastive space, where particles coming from single tracks are close together and particles which are coming from different tracks are far apart. And what we can do now is we can just draw a radius in this space, and then particles in this radius are more likely to be close coming from one particle. And then out of these particles which are in a radius, we can construct a graph. So that's what we saw before. They just have the vertex is the single hit in the detector, and the edge we label as a probability. Okay, and then I can train another machine learning algorithm which takes simulated data and then tries to give a large value, a large probability to edges from particles which really come from hits which really come from a single particle, and low probabilities to hits which come from different particles. And this is exactly what we did. And if you see this graph neural network which is running here, and you go through multiple rounds in the graph neural network, you can see that we can distill the edges, and edges which really look like real particles are like more prominent and have a nice high probability to belonging together. And for example, this and this one are not connected anymore. And on the right side, you can see the model output, and you can see as a histogram. So the y-axis is just how often that happens, and we can see that the network, the high probability, really labels true tracks through the detector. You had a question? The K is, if you have worked with, the question was what is the K? If you work with graph neural networks, you have these rounds in the graph neural network, which means the message is passed through the whole graph, and that's the K. Yeah. So it's basically just a graph turnaround. Yeah. Right. So now that we have labeled these edges, we still don't have tracks, right? Because there are still hits which are like have at least a probability, which are not fitting together. So what we need is tracks which connect multiple hits and represent a whole particle. And what we can do now is we can use standard pruning algorithms, and these pruning algorithms prune away basically the low edges with the low probability, and we're left with the tracks. So as you've seen, this was like a very custom algorithm which runs directly on the hit data, or can run directly on the hit data from our tracker, and can construct these tracks. Okay, that was what we call the tracking. The second one, if you recall, we had the tracking, and second one we had the what we call the particle flow. We have these tracks now here in the middle, and we have to connect these tracks with the hits in the calorimeter. So this is where the particles are then fully absorbed. The hard thing is, that's not a trivial problem, because first of all, there's a lot going on in the detector. So we have to split which tracks correspond to which clusters. And then also the track is measuring the energy, and also the cluster is measuring the energy. And there is no super easy way to connect the energy information from the track and from the cluster, because depending on the energy, the information is like has a high uncertainty or has a low uncertainty. And what we've come up with is the particle flow algorithm, and the particle flow algorithm takes the informations of the tracks and the clusters and embeds them into what we call a hypergraph. I think the graph is a well-known concept where you have different nodes which can represent properties or numbers, and then you can have edges which represent connections or relations between the different nodes. A hypergraph is almost the same, but in a hypergraph you can connect multiple nodes with one edge. So for example, if you see this blue edge here, it doesn't only connect the green and the red dot, but it connects the green, the red, and the yellow dot. So it's just a more abstract concept of a graph. And if I have formulated my challenge into this, making an assignment between the tracks and the clusters is as easy as solving this hypergraph, because in this hypergraph I already have all the edges, and now I only need to figure out what edges represent particles, right? If I have a particle here, this edge in my graph should be the edge between the blue and the yellow. And if I had another particle right here, then the other particle would be represented by the hyperedge between the orange, the green, and red. So, yes.
With machine learning, right, you're selecting high probability of events, but seems like what you're looking for are low probability events. Therefore, is there a chance you're chucking away kind of rare events and forcing them into a pattern that's matching a high probability?
Yeah.
Because of the algorithm.
Yeah. So the question was that with machine learning, we usually focus on high probability events. And we are looking for, in general, physics which have low probability, so do not occur so often. And the question is, are we optimal to the physics we want to observe? I think the answer is that if you have your trained machine learning algorithm, you can decide yourself where to put the threshold, right? You can only not be biased to, or you shouldn't be biased to a particular region in the phase space. Most of the trainings use simulated data. There are some algorithms which use recorded data. We'll see some later, but most of the algorithms use simulated data, and then we can decide which energy ranges we look at. Yeah. All right. So solving this hypergraph problem is now just solving the assignment. So we can construct this two-dimensional matrix between the original particles in the original hits and clusters in the detector and these hypergraph edges which correspond to particles. And then we can train another algorithm which predicts this matrix. Is basically the matrix is just a connection of the hypergraph edges, and then we can just solve the assignment with a Micros algorithm or whatever algorithms we have to solve assignment problems. And then I have reconstructed my particles. So first I had the tracks, and now I can assign the tracks to clusters. So that's the two applications I wanted to show you on the experiment side. That's like the tracking and the particle flow. And now next we want to have the same data basically, but from the theory through a simulation. So let's go to the theory part. You already saw that that's the exact same process I had in the beginning, where we are interested in the hard process. So that's only the red one. But there is a lot of what we call showering and hadronization happening around with the physics we already know, but it's pretty most of we know, but it's pretty messy. And then there's the whole detector interaction. So the question, if I have my particles coming out of my process, how do they interact with my detector, and what is actually the readout I get, which is the thing I can compare. When we do the simulations, what we did for a long time and still are doing for the many of the official simulations is we exactly have this process in the simulation chain. So you have the simulation of the hard process, which is actually where all the physics goes in, and which is pretty simple. It's like solving some equations and so on, but you can do it on your notebook, like 1,000 events in a couple of seconds. That's no problem. Then you have the showering hadronization, which gets a little bit more complicated because just as more particles, but we parameterize a lot of these challenges. So we don't have like a first principles theory calculation of how particles undergo showering hadronization, but we have like numeric models how this happens. And then in the last step, I need to see how these showers and hadronized particles interact with my detector. And this is a really hard problem because you need all the information of your detector, and we have lists of every material which is at our detectors, everywhere in the detector, with where all the cables run and so on. You have to know everything all about this, and you have to know how single particles interact with these materials. And now think about how many particles are, for example, in this wooden box, right? You need to basically simulate how the particles all interact with, like if a particle goes through, how it interacts with not all of them, but like you have to have a fundamental model how this happens and what you would read out in the detector. And this is why the detector interaction is the most complicated part for us, or most challenging part, and it takes 100 seconds per event. So now if you compare this, we make 30 million collisions each second on the detector side, and if we simulate this, we need 100 seconds per event to like compare. There's like a giant mismatch. So our first objective when we talk about simulations is to make the last one fast. And how we can make things fast, we have seen a lot of development with like using machine learning for fast inference and stuff like this. It can run on GPU, it can run on a TPU or whatever. So if you have your whole model of how the interaction of the particles with the detector happens in a machine learning model, maybe it goes faster because it's an efficient parameterization. And we see that it is, so we can have speedups of the interaction with the detector of like a factor of 1000 or even more, depending on the process. Now you're saying, but how do I teach my machine learning model what the real world looks like? So we have some data, which is either simulated or recorded data even. And then we put this into a machine learning generative model, and we see which options we have and how we can train them in a second. And then we can oversample basically what we have measured. Oversampling, so the machine learning model is not generating any new information. It shouldn't, because we want to have a simulation of what's actually happening around in the world. So the generative model should not hallucinate or something like this, even if with the architectures that we use, that's almost not possible. But we can sample and interpolate like the high dimensional distributions of the particles in the detector. And we can use this with multiple different models. For example, we've generated adversarial networks, variational autoencoders, normalizing flows, diffusion models, and so on. We'll see an example of the generative adversarial networks and the diffusion models in a bit.
Are your simulations more compute bound versus memory limited or IO bound limited?
Yes, that's right. All right, so what's the working, the question was, is our generation compute limited? And the answer is yes. So what's the working principle of a machine learning based generator? If we look at generation, even if you think about how you as a human come up with something, so there's always some random component to it at the beginning, right? If you want to make a painting, you cannot always make the same painting just because there's some random fluctuation. And then you have an internal model of whatever you want to draw, and you transform basically the original random representation in whatever space it is into something which looks meaningful in any way. And the question is, how do you do this transformation? And this transformation is just a mathematical function which works in this very high dimensional space. So we're coming up with a random distribution of data and end up with, that's actually a picture of a particle hitting, two particles hitting one of the calorimeters. So that's exactly what we want to in the end. And then I can just use different random numbers. And if I use the same functional form, then I will also have a meaningful representation in the next picture. One approach how we can do this, and one approach which is very fast, which is nice for us, is generative adversarial networks. And I'm sure many of you have seen generative adversarial networks. They've also in the industry been quite large some years ago. And the basic idea is you start with this random noise, and you put this random noise in a generator, and you get out some generated data. And then you have a second network, which we call critic, for example. And this critic network then looks at if the network can find a difference between the generated data and the simulations. And if it can find a difference, then the generator is doing a bad job. And if it cannot find a difference, then the generator is doing a very good job. And there's like a scheme how you can train these networks and how you can inform the generator from what the critic knows about the data. That's what generative adversarial networks are doing, and we've been doing this. And that's actually one of the networks which is currently running in the simulation of the Atlas experiment in a subpart. And you can see the simulated data which we have with the normal simulation that we had before, which is called GEANT4, is like the model of the detector. And we can compare this to the blue line, which is the generative adversarial network. And what we see here on the x-axis is just the energy of the shower which goes into the detector, and on the y-axis we see like how often this happens. And we can see that the blue line pretty nicely matches the data. But we can also see that we have some deficiencies, like almost at the order of like 40% in some parts of the phase space when we model these showers with the gun. So it is very fast, yes, but it's not 100% optimal. At this point, I want to make one point about accuracy. And we had the question before about how often actually something interesting happens, like a little bit in this direction. And here we can see the proton-proton collision. So that's the most technical plot. And when I first saw this plot some years ago, I was completely overwhelmed. But stick with me, it's pretty easily actually. And it shows the whole measurement program of the Atlas experiment at the LHC. So what you can see on the x-axis and what you can see in the different dots is different physics processes. So for example, you can have defined the physics process of you have just two protons which are colliding, doing anything. And then you can talk about, okay, maybe it's interesting to look at one of the 17 particles, the top quark. And how often does the process happen where two top quarks are created? Okay, that's just another physics process. And we have a plethora of these different physics processes which are happening in the detector. And I see the different processes in the different dots on the x-axis. And on the y-axis, I can see the production rate. So how often that happens relative. And I can see that the proton-proton collision happens about 10 to the factor of 11 times compared to the really interesting physics, which interests us, which is like 10 to the minus 1. So we have a rate between 1 to 10 to the power of 12. That's a 10 with 12 zeros. So this is actually why we have these enormous data rates, so we have these enormous amount of collisions, and why we need to skim through most of them very, very quickly, but they do not interest us in the long run, because usually they contain physics which have been researched years ago, right? So like Collider 20, 30 years ago, they researched more the low energetic stuff. Now the low energetic stuff has been figured out by them, and we're going to the more high energetic stuff, but because we cannot change the physics which are going on, we have to throw away the low energetics. So that's exactly why our data rates are so high. And now if you compare this
So from the generative image, I guess is
yes,
the probability distribution over your sensors, I guess, right? To this plot here.
yes. So the question was, how do we go from the simulated, the image, to this distribution right here? This was just an interlude to make clear how good we have to be in terms of accuracy when we model something. We'll see the comparison of the theory and the experiment in the last part of the talk, which comes in like 2-3 minutes. Yeah. All right. If you want to like compare this to a generative approach, which I did on ChatGPT, then and you want to construct a background data set. So imagine you have the task of finding like a cat and like a dog in a cat data set, and you know that your physics is 1 in 10 to the power of 12 dogs, right? And this is my background data set. I mean, this looks pretty good. It looks pretty cat-like, but there is already one dog in there. I don't know if you found it. I smuggled them in. But now imagine the accuracy you need for 10 to the power of 12. So we really need to be more accurate than the generative adversarial networks. And this is why our current best approach is conditional flow matching models. And many or some of you have probably worked with conditional flow matching. It's a more rigorous approach to go from the random in the beginning. So here you have the distribution of the random numbers, which is just a Gaussian function, to the physical distribution in the end. So instead of having this very unregularized or pretty unregularized approach where we have the generative adversarial networks training against each other, have this like oscillating training behavior, we now learn directly the vector field, which would transform a random distribution in the final distribution we want, because this final distribution that we want is actually pretty regularized. It's very high dimensional, so we have the whatever number of outputs you're currently looking at in your study, but it's very regularized. I mean, the underlying distribution and the nature distribution always stays the same. So we have this CFM model, and this CFM model learns basically how to transform one distribution into the other. So the CFM model would give you over, it's like we call it the time dimension, the x dimension, how to transform one distribution to the other.
What we would call it the fusion network.
We call it flow matching, but I mean, they're very related. Yeah. So what we have here is one of the first approaches, which one of the current best approaches, which is called the Calodream approach. And that's what I just presented to you. And you can see that the Calodream is actually much more much more accurate than the gun model we had before. So here we have like a 1% up to 10% efficiency, but this is like the region where we have less data. All right, so now we have our theory part. Basically, I showed you two different approaches how we can use machine learning to make simulation faster while still keeping it accurate with the conditional flow model. So now we answer your question and we come to the last part of the talk. How can we actually now make the comparison between the experiment data and the theory data?
For people taking notes, would you mind posting the slides, the link in the meetup site at the bottom of the webpage for this event?
Sure.
There's a comment section.
Yes, I will post my slides in the meetup in the comment section tonight. All right, so the question is, how can we compare these two? And so now we have very high dimensional distributions. We have like 100 dimensional distributions. If we look at the 100 million dimensional distributions, if we look at the raw detectors readouts, we have a little bit less dimensional distributions, but still very high dimensional. If we reconstruct particles and so on, so instead of like looking at the bare hits, we look at the particles. And we have even a little bit lower if we put in our physics intuition about how particles, how we can combine particles and so on. And for years, we've been doing this. So we had PhD students who would sit in their computers and combine particles and see how they can have good distributions, how we can distinguish between the known models and unknown models and so on. But nowadays, most of this is also done with machine learning. So we use a neural network in comparing the theory which we had in the beginning. Oh, don't see my cursor anymore.
When you get a chance, there's a question from the room audience.
Yeah, sure.
Isn't there some risk of confirmation bias, perhaps due to training on unexpected interactions, and we'll miss some truly unusual interaction, which might be thrown out, thinking it might be something like cosmic rays?
Yes, that's a very good question. So the question was, if there are some things in the simulated data, for example, that we train on, which look like the stuff we want to find, but wrongly identify, then we could have a large bias towards these particular signals. That's how I understood or not find these signals. That's how I understood the question. And that's true. That's one of the points why the simulations need to be so accurate. So now that we compare basically what we know of the world with what we don't know, so I put here one of my theory colleagues, and they often come up with new models. So they would come to my office and tell me, okay, I have this great idea for this new model that has to be the extension of what we know, right? And I say, okay, we can compare if your extension makes sense with the current model. And I will use the simulations of what we know until now and the simulations of the new model my colleague has come up with. And I will train just a classifying neural network to distinguish between what we know until now and the new theory. And then in the next step, I can just use the recorded data and I can put the recorded data into my model. And then I can see, okay, what does the model say? Is this like a known thing or is this an unknown thing? And then I can count the unknown things. We do this, there's a very, very low level view, a very, very high level overview of what has been done, but that's basically the structure of our analysis. So we train some models and we have to look that they're bias free. We have to see that all the systematic uncertainties are taken care of and so on. But it's a high level overview. We train a model distinguishing between the known and the unknown, and then we just look in the data and look how often we get the unknown. One thing which makes this very complicated is that all these processes underlie quantum mechanics. So if you would train an image classifier, which would classify a cat and a dog, that would be not so hard, right? Because you know what a cat and what a dog looks like. But if you have a quantum mechanical cat and a quantum mechanical dog, then each dog looks a little bit like a cat and each cat looks a little bit like a dog. So it is very complicated and there's a lot of like statistics going into the whole thing that we cannot describe single events, but we have to describe probability distributions of events. Yes.
I had a completely different question, but it can't be cheap to run these simulations. So how does the financial and funding
Okay, the question was does the financial and funding part work? I would like to come to this to the end because it would derail us now a little bit, but I'm happy to talk about this part as well. All right, so we do this, and we've been doing this for years and years and years. So the data taking from these experiments started in 2011. We're still taking data. The collider is running round and round and round whole year, every day. Some years are shut down where we make technical adjustments and so on. But we have taken a lot of data, and until now we have not found a single serious deviation from what we knew before we did this. So why is that? If we think about new models which could exist in the universe, we can draw like a space of possible new physics. So that's just a very high dimensional concept of, okay, there could be some new models which extend what we are currently seeing in the world. And what we've been doing until now is to make specific searches. So look for one model, train a classifier for this particular model, and see if this model exists. We didn't find something. We go to the next model, and so on. And by now, the models we have excluded is in the thousands. And each exclusion of this model is basically one PhD thesis. Okay? This is not super efficient in terms of looking for different models. So the reason why I'm here in Berkeley now, and the reason what the specialty of my group and our group is that we're using something which is called anomaly detection. And in this anomaly detection, our only hypothesis is that we are looking for something which is not what we know, right? So an anomaly from the known. That's, I would say, a smart thing to do. The question is, how do you do this? And the way we do this is we are, because we're a machine learning group, trying to ask a machine. We're not going to ChatGPT and ask a machine, obviously, but we're constructing algorithms in a clever way such that they know what the known looks like, and then we can look for differences with what we measure. And we'll look at two different algorithms in the next slides. But first of all, let us take a step back and ask, what is an anomaly? And for us, there are two types of anomalies. There is out-of-distribution anomalies, which would be this big dog. If you see the big dog, you directly know it's an anomaly. You only need one sample, okay? And then there is in-distribution anomalies, where you have like in the distribution an overdensity of events or something like this. So if you look at each single dog in the right picture, you will not know there's an anomaly, but if you look at all the dogs, you will know. And we have two different classes of machine learning algorithms which target those. So first we look at out-of-distribution anomalies. And one approach which we do is using autoencoders. And autoencoders are machine learning architecture where you have all the inputs on the left side. And then just the architecture of your network is such that the data has to be compressed. And then it has to be up-compressed again, like upscaled again in terms of information. And for the data that I train on, the autoencoder will learn this compression. So if I put in all normal dogs, this autoencoder will just learn to compress the dogs because the autoencoder will learn what a dog looks like, a normal dog in the distribution. But if I look at the last dog, then the autoencoder doesn't really know what to do. So this last dog is so different from all the other dogs that this compression I learned before doesn't really work. So it will uncompress the last dog in a very, very different way. So now we can just compare. We can compare the input picture and we can compare the output picture. The good thing is that these autoencoders can just be trained on the whole data set. If I only have single examples which are different, they will not influence the training of the autoencoder. So I can just take all of my events, put them in, train the autoencoder, and then I can compare between the input and the output.
But earlier you were saying in your presentation, there's like a 10 to the 12th difference between the proton and the things you're interested in.
Yes.
So, you know, when you're training your autoencoders, I guess you're getting rid of all the high frequency stuff. So you're not training your autoencoder to see the high frequency stuff. It's just knowing kind of what's in the realm of the lower frequency. So that way you can still have a chance of finding the infrequent.
Yes. So the question was basically on which type of data the autoencoders are trained, because we have all these high frequency data, which is very often and not super interesting to us, and we have the low frequency events. What we use is usually we have a pre-selection of events. So before training the autoencoder model, you will only have decently interesting events, but most of them have still known physics. So that the anomaly which you could find, so we are still, even if we're throwing away a lot of events at the trigger level, we still have trillions of events which are known physics, but they're super interesting to us still. Yeah. All right, if we do this now, we can plot the difference between the left and right pictures on the x-axis and the number on the y-axis, and most of the events will end up in the normal distribution, and some will have like a very high anomaly score because this compression and decompression does not work. And both collaborations actually now have employed such a model at the trigger level, which is super interesting because most of the data analysis goes on at like the computing level after I run through all the different computing centers and so on. It's offline analysis. This is a real online analysis. So at the rate of 40 million events each second, these events are fed into an FPGA, and this FPGA runs the autoencoder and looks for events which have a high anomaly score. And I can do this, and I can plot the anomaly, the difference basically. So the anomaly score on the x-axis, on the y-axis, I just have the counts, and I can look at the most anomalous events. And the most anomalous events are actually looking super interesting from the one side because it is something that that is not the norm of the distribution. Now the question is, what do I do with this, right? Because I have quantum mechanics. I mean, theoretically, it's possible that it's a super, super weird process which only happens once every whatever decade. It's theoretically possible, but currently both collaborations, CMS and Atlas collaboration, are recording these data sets, and will be super interesting in the future to know actually how we can further analyze those super interesting events.
I just want to ask, when you're autoencoding, are you autoencoding theoretical predictions based on the differential equations and stuff, or autoencoding collections of data that have been gathered?
Yeah, so the question was, when we're autoencoding, are we autoencoding, or is the autoencoder using physical symmetries? Could you?
Well, I guess you'd be using some sort of results that are coming from the
Yes.
mathematical theory or
Yes.
something,
Yeah,
right?
simulation data versus empirical data from.
It would have to be in the same measurement space as physical data, right? You'd have to simulate, I guess, your sensor readings so that you could compare, you could run sensor readings through it, but I mean, I can imagine you take lots and lots of sensor readings, you got your images, and you autoencode those, and now you have something that is capturing the regularities of what you actually measure. And I mean, whatever you run through there is sort of taken from that same distribution, right? But I guess that would put a priority on capturing the center of the distribution in its hidden layers, right? So so I guess you would separate out the anomalies that way, but the other one would be like if you're looking at deviations from some sort of mathematical theory, so your autoencoder is some sort of representation of your theory, and you're looking for things that look very unlikely given the theory. So
He has to be able to repeat the question.
yeah.
All right, I'll try to repeat the question the way I understood it. I think the question was, are we putting in sensor data? Are we putting in some mathematically transformed distribution of events? Is that?
Yeah, I
Let's
can
try to
tell
balance.
where you did that, and you're putting in sensor data.
Okay, yeah, we're putting in sensor data, but it's reconstructed sensor data. So there are some priors actually of like the reconstruction that I showed you, like the track reconstruction and so on. And we need to do this reconstruction to be able to efficiently handle the data. And that's according to our physics views of the world. So you are right that we're putting in the prior that the particles behave, for example, in the curved track through the tracker. We're putting this as a prior. And it could be that there is an anomaly where I have a spiral track in the tracker, or I have there is a very interesting theory. I think it's called quarks, and there are particles which occur in pairs, and they're like oscillating from each other, and you get these like weird tracks. And there is also people looking for these very weird things. We are on this. So actually, on the autoencoders, they are at the core of the data taking. So there's a lot of also organizational work to be done, and I think we would not have something which is this hypothetical at this stage of the detector. So this is more like a rigorous proven reconstruction and so on, which is there. Answer your question?
I think so.
Okay, we can also talk later if not.
To maybe just put it in a slightly different way, is it fair to say that autoencoders are basically trained on known physics? Yes. And it's kind of like almost like a model that has been trained based on known data. And then, and what you showed in the previous slide is basically kind of like inference, where as experiments are happening and as new data is coming in, it is going through this model and it's throwing out anomalies, and the anomaly, or it's throwing out a bunch of data, but you're interested in only in the anomalies because that is potentially new physics.
Right. The question was, can you say that the autoencoders are trained on known physics? And that's absolutely the case, because we have not found anything yet which is different to our theory. So our assumption is that most of the events that we saw until now, not all of the events, my personal assumption is there, I hope, some events which are not according to the theory, but most of them are through the theory. Otherwise, we would have found something else or some deviation from our model. So if we take all these events, put them into the autoencoder, train the autoencoder, it will look for deviations of the known stuff. Yeah. All right, we saw this, and now we can switch gears a little bit. So we looked about the out of distribution anomaly. Now, how can we find in distribution anomalies? And that's one of the specialties we've been working on for the past years. So how can you find this? We first define what we call a sideband region and a signal region, and this is like a first assumption about signal region and sideband regions, which doesn't have any reason yet, but we will lower this assumption in a couple of minutes, so you can see that we could find every signal region in the possible space. So we just define a signal region and a sideband region, and our assumption is that the signal region, if there is some signal, has the signal, and the sideband does not. That's just an assumption. Okay, there is no reason for this. And then we look at the sidebands, and we have a generative model. We look at the sidebands and we learn what the sidebands look like. Okay, and then we just use this information to construct data in the signal region. Now I have two data sets. I have the recorded data, which potentially has the in distribution anomaly, and I have the complete background only estimation data set from a machine learning algorithm, could be, for example, a flow model. And now I can train a classifier, and this classifier can be trained between the background estimation, which only has the background, and the signal and background. And there is one very nice mathematical formulation, which is called, for us, the classification without labels. It means that the likelihood function, which I get out of this, so the distinguishing, like the features out of this, would be exactly the same as if I would look at the background versus the actual signal distribution. Okay, that's just because that's the only difference between the two distributions. So if I train my network, the only difference the network can find is exactly what's the anomaly, without specifying something about the anomaly besides the region. And now in the next step, we can lower this threshold, because we can just imagine this high dimensional space, this model space, the green blob I showed you, and we can just swoop over the green blob with the signal region and redo our definition of the signal region and the sideband region every time. And we did this. There is a very nice, what we just saw on the x-axis with the dogs. There's a very nice physical interpretation, which, if you look at events which have two jets, so jets are just particles which go in the detector, they mostly contain quarks and so on, and we just sum them up, we get their what we call the mass. their invariant mass. And we know that this invariant mass spectrum is mostly dominated by what we already know. And it has a fixed mathematical form, which is in this case an exponential which is falling. And now I can just define my signal region somewhere, because I know from first principles that if there was an 18th particle and this 18th particle would decay into two of them, it would have a peak somewhere in the distribution. Okay, so the black dots would be somewhere in this distribution. So I can define my signal region, sideband region. I can just train on the background region generative model, compare with the signal region, and do exactly the same what we've done with the dogs. So that's exactly what we did. We defined signal region, sideband region, did a background estimation, and then trained the network, cut on the network. And what I see then is that the peak, so this anomaly, is much higher than it was before. And you can try this on simulated data. So that's not a Nobel Prize, unfortunately. That's only simulated data. The question is, can we get the Nobel Prize in some years? I hope so. Is if you do not have any signal, then you apply this algorithm, and this algorithm gives you a very high probability that is a background only. So that's what the y-axis looks like. It's basically the probability that of the data given the background hypothesis. And if you inject the simulated data, you can see that this probability that it's a background only actually goes up. And at this level, 7 sigma, so we usually have the Gauss function, and you can talk about how many sigmas are you away from the Gauss function, would be 7 sigma. That's like super significant. We usually in physics talk about 5 sigma as our threshold to have a new discovery. All right, so we've seen 2 comparison methods. We've seen the classic analysis in the beginning with the counting. That's what we've been doing for years. And now we're switching gears a little bit, because we have these nice methods giving machine learning and so on to do anomaly detection, both for in-distribution anomalies and out-of-distribution anomalies. And now I am talking for 1 hour and 20 minutes, and we've seen so many machine learning methods and so many networks. The question is, do we really need like a different network for every part of our data analysis? It seems like wasteful, and all are doing physics and all are looking at like similar particles and so on. So there is this idea of foundation model, which is big in industry and also now goes over to physics, where the foundation model, I mean, probably most of you are aware, you have like massive data. You not only have only some training data, but you have all the text of the internet, all the images you can find, all the speech you can get your hands on, and you train this model, which is huge, billions of parameters. And this model has like a internal representation of the world. And this internal representation of the world can then be used to do text generation, Q&A, object recognition, and so on. So the similar idea comes from the physics. I write only massive jet data set, but we can like put in all different data sets, and actually that's like it's different data sets internally, and we put all them in and train them for a particular task. And then this, what we call jet model, is a foundation model which can have different heads and then actually do things like the tracking that we saw, the reconstruction that we saw, generation that we saw, and also the anomaly detection. There's been multiple projects, but one project is OmniLearn, where you can see that on the x-axis, there's like how I fine-tune this foundation model on a different task. It was not trained before. And on the y-axis, I can see how good this model is. And I can see for the dotted line, which is the OmniLearn algorithm, I have a much faster convergence and actually are quite better than if I would train the model from the ground up. So we've seen this comparison of nature and theory going from the detector over the simulation and then the comparison. We've seen all these different machine learning algorithms, and we've seen that we can solve this with machine learning. Thanks so much. And I'm happy to take more questions. Yes.
So when that had the,
Yes.
that's incredible, because like there are some neural networks that you train on just like basic random stuff in industry, and like it can take 5 epochs to get it, and you're doing this with like crazy ass physics. It's like, I don't know, sorry, I just think this is so cool.
You mean like
big size times training set.
Yeah,
So-
yeah, yeah,
So,
yeah, yeah,
what I
yeah,
think is one past the training set. The
Right.
training set is huge.
right.
But-
But still, like, it, I guess I was imagining that would take a lot more epochs, like more cycles through the model, because I mean, 5 is like a kind of standard number for what I see in my industry, so like.
That's right, but it really depends on how you define the epoch and how you define the size of the training data set, which in this case, I'm not 100% aware, like how many jets are used to like fine tune this model in a particular case.
So would these models be less prone to hallucination, given probably the data sets are pretty good? You're gonna clean them up, and
Yes.
it's not like the junk that you find on the internet. This is
Yes.
real experimental data.
Yes. So that's yeah. I asked myself if I should put one slide between differences like in industry and academia or like our data. One of the main differences is that our data is super good because it's all simulated data where at every stage of this simulation, like the simulated data, where at all stages of the simulation process, you have full knowledge about what is currently happening. So we don't have very big problems with like contamination and stuff like this. Yeah.
So, okay, going to the generative models, the variational autoencoder, the GANs and stuff like that. My understanding, if I'm following you right, is you basically have developed a probability distribution of all possible sensor profiles that could occur. And you've developed an algorithm where you can sample one of those sensor profiles at a time, right? And then that sensor profile, it's not clear to me that we know that that's consistent with the standard theory. That's, I mean, it may be that, 20% of the things are actual dark matter particles or something that cause this distribution to occur, some weird physics that we don't know, but it's managed to learn that weird physics.
Yeah.
And now we have a model, a distribution of whatever it is the LHC does.
Right.
So I guess I'm having trouble making the connection of how we go from there to the physics, or how we know that,
All right. So the question was, how can we be sure that the generative model doesn't model things we haven't understood yet?
Yeah.
Basically. So if the generative model just models the dark matter interactions, then we have not found any, anything. And I think I have a backup slide for a similar thing. So that is the gun which you saw in the beginning. And I want to make 2 points. So first of all, we're always comparing to the low-level simulation, which actually models every interaction with the detector and so on that we know of, and completely parameterizes all the interactions. And we have been comparing the this model to the data for a very long time. So we know that for the stuff that we know of, it looks like this. Yeah. And then when we
because the critic says it can't distinguish between the theory.
No, because we've been we know that the normal simulation looks like the data because we've been looking at the differences between the two for many years. So we know that the simulation for what we know of is quite accurate. We don't know actually if the simulation is quite accurate for what we don't know of. And it could be that the new particles just look completely different and are absorbed in the distribution of whatever we are simulating, but then we just couldn't see it. If the new physics would exactly look like the physics that we have and basically only occur once every decade or whatever, one event, we couldn't find it. But if it looks the same, then we can look for the ratio between the new physics and the new physics and the old physics and what we actually measure, and there would be a difference in the ratio. I don't know if that goes into the direction to answer.
How do you detect the difference between the theory and these sampled images, I guess? Is it because you're using the critic that you trained to differentiate between them, if you really can't tell the difference? then
No,
you're-
we're using a different network. So that's the question was, how do we detect the difference between the simulated data and the recorded data, basically? So we are looking directly at higher level distributions of this concept. So we have this whole process I showed you with the reconstruction to go to lower level representations of your process of the physics events, and then we can compare the distributions of these lower level of these or higher level features. For example, I showed you these two jets, and if we sum them up, all the reconstruction, all the stuff, we get one number out at the end, and that's like this one number is representative for the physics we are currently looking at for one single event. And then we can just look at the distribution for all the simulation and for all the data. And we can see if we find a difference.
Are those higher level things hand designed?
Yeah, so they have been hand designed for a long time, but then like 10 years ago, we started using neural networks to basically design them by using classifiers between what we know and the new physics. And these classifiers then basically autonomously create these higher level representations. And then what you can do is you either look at the distributions directly. I think I have a plot of one of the distributions. Sorry for the skipping. I don't. Okay, sorry for that. So then we look at the distributions of these network representations of the events for the simulated data and what we actually record. Yeah, and then like if you want to know the statistical process, then we have we construct a likelihood function of how likely basically the new distribution is compared to our reference, and then we can do all the statistical analysis and so on.
In all of your examples, you use CERN hardware and the linear accelerator. I'm thinking, my question is does it make any sense to consider the use of this with the Stanford linear accelerator data application there? Just comment.
Yeah, so the question was, in all my applications, I use the LHC data. Would it make sense to use things at the SLAC, for example, SLAC linear accelerator? The answer is it depends highly on what you do. Some of these anomaly detection methods are now employed on older collider data, for example, from the Hera detector and so on, because all this data is preserved, or most of the data is preserved. So you can just have all for the LHC data that's very, very large. We talked about this. You need large computing centers. You need things like Perlmutter from Berkeley Lab and stuff like this to analyze it. For the Hera data, I can put it on my laptop basically and analyze it. So that's very, very nice, very handy. And it makes sense to employ special anomaly detection, for example, on this, because they looked at a different energy region, and maybe in this different energy region, we find something interesting. For the SLAC linear accelerator, as I'm not working with SLAC as of now, as far as I know, it's a completely different data, which is used mostly for solid state physicists. So I think they now they're not looking at particle collisions, but this is I'm not 100% sure by what I'm saying now, but I think they mostly create radiation to be used to look at materials and so on. So we will not use something like this.
Not particle physics.
It's not particle physics, yeah.
So could you comment on, like, you talk about a lot of neural networks all over the place. Could you comment on like how big these networks are,
yeah,
and the precision of the data you get, like how many bits of precision? So
yeah. So the question was, what's the bits of precision that we have for our data, and what's the network sizes and so on? It highly depends, and it's very different from where you are looking at. If you have a network which runs on an FPGA directly at your trigger, cannot be big. We'll only have like a couple of hundred nodes in the autoencoder and so on. But then if you go for the foundation models, they are like the billions of parameters because they really need to be big. And then for the precision, it also depends. If you have from the first readouts, they can be like just binary for the first readouts, but then you combine this data before it goes to an algorithm. And what we mostly work with is just 32. Yeah. That's like ours, like a standard precision. For some things you want double precision and so on, but like standard. Yeah.
Okay, but nothing below 30.
Question was, do we use something below 32? There are some projects at the LHC currently which use like binarized neural networks, where the weights themselves are just bit value. Yeah.
Is for industry application of the thing.
Yeah. Do I have any ideas for industry applications? I think many ideas. Most of them are in the anomaly detection scope. I think anomaly detection is pretty interesting. There's a lot of connection potential. So if someone wants to talk about anomaly detection, I really appreciate it. Like exchanging ideas there. And I think in the industry, you like, as far as I imagine, if you have a self-driving car, you will not encounter a pink elephant on the street, right? But there are a lot of maybe, but very unfortunate.
Major breakers.
Maybe. So you will not encounter this. So it's not so much the out of distribution anomalies, but I think in the in distribution anomalies, it could be very interesting to like look at how you can optimize a self-driving car algorithm according to what is like in distribution, but not so likely to happen. Stuff like this. Yeah. Also, I think on the at least I know for a lot of like physicists who go into industry, I think there's a lot of potential for like just the mathematical base of it, because when we do this, we cannot make a wrong discovery. A wrong discovery would mean that we would build the next collider at the wrong energy point or something like this, because we would make like a wrong discovery, a wrong paper, a wrong particle discovered would be like devastating for the whole field. So our mathematical methods have to be very, very accurate to describe exactly the sensitivities and exactly the significances that we see at the end. And I think also on this like more mathematical frontier, there's a lot of potential. Yeah.
You had a reference slide that wasn't up for very long.
Yes.
What was the paper that was showing, you're talking about an algorithm that you have the dogs on the two sides and the band in the middle with the dark dogs. You're trying to do the labeling. What was that algorithm called again?
The question was, I had the citation slide not up for so long. It's multiple. So there's the classification without labels, which is the koala algorithm.
So it's called classification without labels.
Classification without labels, that's right. I can look afterwards. I'm sorry, it's too many to read through for me now, but yeah. It should be number 18 is one instance of the classification without labels. And then you see the algorithm 19 is where we applied this algorithm with the background estimation to Atlas data. So if you're interested in the algorithm that compares, you would like to have 18. If you're interested in the background estimation part, more 19 and the other references there. Yeah.
More for finance, fraud detection, other applications.
Yeah.
On anomaly detection, isn't your critic for a GAN, isn't that an anomaly detector?
So the question was, isn't the critic for the GAN an anomaly detector? I would say not, because yes, that's a super interesting question. And there is something which is called generative anomaly detection, which has been coming up for the last half a year, where you actually train a generator and you say, okay, this generator basically already describes my underlying distribution. So from this standpoint, you're absolutely right. And so exactly this idea. For the GAN example, I would say not, because the GAN example, if the generator would be good enough, it could model like the underlying distribution, and they're trained to have exactly underlying distribution, but you're exactly thinking in the right direction. Yeah. You're approximating your underlying distribution by the generative model. Yeah. I don't care.
Okay, so, when you're looking for something that's so low probability, like, does it, do errors and other things come? And become a problem in the sense of like, hey, maybe I'm seeing something, you know, that's some kind of just mistake in a bunch of, and also, do things need to be like reproducible, like if you were to find something, and how would you?
Yes. So the question is twofold. The first one is, how do we deal with uncertainties? And we can spend another 3 hours on uncertainties, at least. And the same question is, how about the reproducibility and everything? So I'll answer the first one first. Uncertainties are one of the most important things in these analyses. And if you do an analysis, they like a full-fledged analysis with CMS or Atlas data is anywhere between 3 and 5 years until publication. So there's a lot of like going into the research process and also in the publication process. And I would say 30% of them are making sure that the systematic uncertainties actually describe what they should describe. And they're so fine granular that I showed you the detectors in the beginning, which record the energy of the particles, like the calorimeters, right? And all of them have a different response depending on the energy. So for a single part of the calorimeter, basically, you have to know what's the uncertainty on the energy measurement through the whole analysis, like for each single event. And that's like the level of how we try to get our, like how accurate we try to get our systematic uncertainties, that we can like get the energy measurement of a single jet at the beginning, plus minus 10% or whatever, reflected in the final result, which is in the paper, which is only like one central number plus minus the uncertainty on this. Does that go in the right direction?
Yeah, it gives me that.
Guess not, yeah. And then the second part of your question was the reproducibility of everything. Yes, there is a lot of efforts going on to reproducibility, and I'm actually spent the last like 2 years working into this direction. We have custom systems which ensure the reproducibility of the analysis, so that a person could come in, I don't know, 20 years and say, okay, I have this incredible idea for this new model. I want to redo what they've been doing 20 years ago, and they can basically give the new model into the system, and the system will rerun this particular model with the analysis. At least that's the idea. We're not like, I cannot look into the future, but we're setting up everything to be reproducible in this sense, also in terms of like data preservation. I'm personally doing this for the anomaly detection, because in anomaly detection, it gets a little bit more difficult because you're changing the algorithm. So you cannot rerun the same network you trained 20 years before in 20 years if you give them different data, because our anomaly detection algorithms are looking for anomalies within the data, like within the data. We're not looking at the data from the outside, but we're trying to learn what are the anomalies from the data. So if someone gives me new data from like data recorded in 20 years, wants to rerun my analysis, they need to like retrain all the networks, do all the validation stuff again, and so on. So there's I don't know if I have the paper on the citations, but I can give it to you if you're interested.
I was gonna ask, when I worked in security, we could find anomalies or outliers, but not all of them would be alert worthy. Some of them may be unusual behavior, but it may not be a security threat.
Yes.
On your data, do you have very few outliers, or do you ever get in a situation where you get so many outliers, you have to filter and prioritize which ones are more relevant for investigation?
Yeah, the question was, when you compare to a security application, some of the outliers, some of the anomalies are not noteworthy, and how's the situation for us, basically? How's the what's the ratio between noteworthy and unworthy. For autoencoders, this is mostly driven by the technical capabilities of the data stream. So I have to decide how many events I want to, like, I can keep, and how many events I can store to disk. And up until this anomaly score, I basically push out everything. But the analyses of these data sets are not super far progressed. So I expect that there's a lot more coming from like these, like on top of analyzing the data sets which come from these autoencoders. There's a lot more to come, but for now we just keep all the most anomalous things that we can, and I think it's actually the same. I imagine it to be in security applications, because there I can say, okay, I have a team of 10 people who can investigate them closer in like this and this rate, right? So I can put the threshold exactly where I have this trigger rate. Yeah.
So in the in distribution anomalies, I guess my interpretation that as I have what you said you did was you identify a subset of your space, and then you train on everything that's outside of that subset. And then you say, did the network generalize into that subset? And is the actual distribution observed different from the generalization of the network?
Right.
Did I say that right?
You said that right. Yeah.
Okay.
Okay.
So I'm wondering if you could use something like adversarial learning techniques on your learned network to find, I'm assuming you identify the subset manually right now, like a theory or something. I was wondering if you use adversarial techniques to kind of find, a subset region that would sort of maximally, cause a difference, because it sort of be the adversarial subset that causes the greatest difference from your background generalization.
I'm not 100% sure if I understand the idea.
I would suggest we need to be out of the room at 9 o'clock as a hard stop, so maybe thank the speaker. We can continue any conversations.
That's good.
Offline.
Sounds good.
Okay.
If the conversations continue past 9, maybe handle them outside, so we can lock up the room, turn off the lights. But thank you. You've had a very passionate audience.
Yeah. Thank you very much. It was great talk.
Generate a lot of good content, so thank you very much. You can just go ahead and close down the recording.
If you want.
Thank you.
Yeah.
Okay.
I would ask any
Thanks.
volunteers,
grab the
some of the
Yeah, sure.
chairs that have no wheels, that we can stack them up in the back line by where the carpet line is.
Very well done.
Help with the
Don't,
kindly appreciated.
So,
They'll give you the most expensive piece of plastic ever to hold off to your life. It's usually, yeah, a lot, but usually.
alrighty.
Appreciate it. That was great.
Thank you very much. Appreciate it. It was a lot of fun. Very, very.
I know a thing or two.
Some things. I've been doing it for quite some time.
Have you heard of the bark
Get us some pizza, yeah.
collider?
Barclay.
So once the bark goes all the way around,
Uh-huh.
there will be collisions
Oh wow.
Uh,
I hope not. I hope not.
about once every year.
Yeah, so in an adversarial technique, you
Yeah.
would find the input that kind of causes the maximal error, right, in the like a classification. So, you could take an image and you could figure out how to alter the image so that it
Like in the serial attack.
like it thinks this airplane's a penguin.
Yeah.
And it's, sometimes a very minor difference can cause it. And you do that through kind of a back propagation method. You sort of optimize on
Yeah.
changing it.
So-
So I was thinking if you took your network that's been trained maybe on all the data, and now what you want to do is you want to find some, likelihood function, some threshold that
Right.
you want to find some way of defining that. Maybe you would do that through some parameterization that describes a subset. And so then you would basically use backprop to tune that so that you get the maximal divergence from your
Right.
background. And so you end up coming up with a likelihood
Yeah.
thing that kind of finds where the maximal difference is. Because if you like manually tried this one and tried that one, you know, until you found the hit, you'd be, you know,
Right.
it'd take a long time.
Yeah.
but-
So I think I understand what you mean now. Let me just double share.
Yeah,
Uh,
I was just thinking of a way to.
yeah, that's very nice. I
way to
appreciate.
figure in
Appreciate it.
distribution. I was thinking about what counts as an in distribution.
So you basically,
but-
as far as I understand, proposing a clever way to scan this space.
yeah,
Is that right?
to kind of maximize
Right,
the
right.
yeah.
So the thing is that this space is open,
Uh-huh.
right? So we cannot say, okay, we want to. So as far as I'm, it's a very good idea. The idea is to best distribute the points, right? So you would say, what are the points which are most different from what we're currently seeing?
Uh-huh.
But I would say there is no prior that those points are actually like
Meaningful.
meaningful,
Yeah.
right?
Yeah, that's
and-
probably true.
And but there is a meaning that they're easy. So
Yeah.
maybe we can solve the easy ones first,
Yeah.
right? So that's an interesting idea. People have coming up with more classic algorithms to like have this space. But then on the other hand, I think also the space is open. So there will also be always be a model which is like infinitely different compared to what we currently observe
Yeah.
than all the other models. But it's an interesting idea. Like how can we
Yeah.
how can we structure this space? I've actually started today with a project with one of my PhD students to like trying to optimally convert this space in something regularized where you can like use different methods to like divert it and so on.
Yeah.
But it's a great idea, yeah.
Yeah. It's kind of the induction problem in a way. you know,
Right,
like
right.
like the groove.
Yeah.
You know, Grew that
What's Grew?
Goodman. Oh, this philosopher named Goodman wrote the stuff about induction, and he came up with the idea of Grew, which is green. I can't remember what exactly it is, but like green sometimes, blue other times, and
Okay.
it's like I can't remember what the conditional is, but it's kind of like, you know, why do you learn the concepts of green and blue and not this Grew and Bleen instead? You know, which is logically equivalent, but you know, to us it feels different. And unless you have some sort of other similarity metric or something imposed, you can't really say one's better than the other.
Right.
You know, and you know, there are these things like the size of the hypothesis space.
Yeah.
You
Right.
know,
Right.
Vapnik-Chervenescus dimension and stuff like that. It kind
If
of characterize.
it's open, then it's
Yeah.
not. There is a lot of things. A lot of rigorous arguments about Occam's razor,
Yeah.
because there are infinitely many theory, like really
Yeah.
infinitely many, which are super complicated, right?
Yeah.
So theorists usually
Minute countdown.
start with the theory and use Occam's razor to use the simplest theory, because for us as humans,
Yeah.
like those theories are in a way beautiful, which
Yeah.
doesn't mean they have to be right. So it's
Yeah.
like there's a lot of
Simple's
almost
relative.
fire-
Simple's relative to whatever language you're using.
right,
But yeah.
right, yeah. That's my standpoint on
Yeah,
it.
yeah.
But what was the
Okay.
GRU you said?
Grew and Bleen. Yeah, it's a guy named Goodman. He was a philosopher. I can't remember his first name.
Okay,
But yeah, it's kind of a classic thing on induction.